Okay, so now that we know that in an ideal gas, every molecule carries an average kinetic energy, which is 3/2 of the Boltzmann constant times the temperature, so that each degree of freedom carries 1/2 of kT on average. We are going to explore the more general result, which is the equipartition theorem. So let me just write it here: equipartition, long word, partition theorem. Okay, so let's see what this says. And we're not going to prove it, like I said before, because we would need to introduce more things that we don't have time to discuss. But essentially, it says that if you have any system, say a system with like that, so it's a Hamiltonian of the system. Remember, that's the sum of the kinetic energy plus the potential energy. And remember, Hamiltonian is it is actually a Legendre transform of the Lagrangian. It is a function. As a function, it's a function of a set of generalized coordinates x1, x2, xn, and a set of corresponding conjugate momenta. So p1, p2, pn. Okay, so that's the functional dependence of it, and it is kinetic plus potential energy. Okay. So what the equipartition theorem says is if your system is in thermal equilibrium, then this kind of thing holds. Okay, so the partial derivative of the Hamiltonian with respect to any of the coordinates times the coordinate, when you take an average, or just the same if you were to take instead of the coordinate any momentum. Let's just see pj, partial of h with respect to pj, just to emphasize that it could be any number. These guys are always, all of them, going to equal to kT if the system is in thermal equilibrium. Okay, so that's just the kind of main result of the theorem, and this is what we have actually seen in the calculation we just did. Okay, so the calculation is consistent with this result, and let's see why. The Hamiltonian in our case is of this form, 1/2, and then there is this 1/m. In general, we could have here any constant. Okay, we could call this alpha or whatever, but in this case we have 1 over the mass. And here is p1 squared, or px squared if you like, p2 squared or y, and p3 squared or z. Okay, so that's our Hamiltonian for a free particle without any potential energy. There's no confining potential or interactions or anything like that, because we have an ideal gas. So here, when you apply this result, okay, you know then that pj, partial derivative of h with respect to pj, on average, what is this going to be? Well, take the partial derivative of the Hamiltonian that's written here with respect to pj, and what you get is 1/2m twice pj, okay? And the whole thing is multiplied, like I'm saying, by pj, so let's just write it here. This is this pj here. So we take the average of this goes with that, and what we have is 1/m pj squared on average. This thing, according to the theorem, equals kT. Okay, so what we see is that if we take the average energy of every molecule in the ideal gas, what we're going to get is 1/2 of kT 3 times. Okay, that's just what we're going to get, because we have the 1/2 here multiplying, and the 1/m p1 squared is kT, the 1/m p2 squared is kT again, and so on. And this is exactly what we found before. Okay, so this thing, which is actually equal to the kinetic energy average, because we don't have potential energy, is 3/2 of times kT. Okay, so this is what we just saw. But we can use this result in more complicated Hamiltonians with more terms. Okay, and this is what we're going to do now. So just going back to the monatomic gas, let's calculate the heat capacity. So let's just write here heat capacity. Well, let's just abbreviate. So heat capacity at constant volume for monatomic gases. Monatomic gases. So I was thinking maybe I should put here CV and CP. CP. Okay, so how do we calculate this? Well, you know that the internal energy must be for a mole of gas, so always thinking of 1 mole in this case, it would be the number of atoms in 1 mole, which you know is Avogadro number, times the average energy per molecule, okay, which we calculated before. In this case is N times the kinetic energy per molecule. And this is Avogadro's number here. And what this is 3/2 of K times NA times T. Remember that this thing here is nothing but the ideal gas constant R, okay? So remember also that we know that the partial derivative of the interval energy with respect to temperature at constant volume equals the heat capacity at constant volume, okay, by definition. So this is the interval energy, depends only on temperature. Again, it's an ideal gas. So what you find here is that the derivative with respect to temperature is 3/2 of R, which is something, if you remember, we said in the very beginning of the module, okay? The heat capacity at constant volume of a monatomic gas, 3/2 of the ideal gas constant, or the gas constant. And how do we calculate Cp? Well, remember Meyer's relation for an ideal gas, which has the simplest possible form, which is Cp equals Cv plus R, okay? In this case, this means that Cp is 5/2 of R, which again was the result that we quoted in the beginning of the module, and I promised that we would prove it. So here's the proof. Okay, that's for a monatomic gas, but now let's see what happens with the diatomic gas. So in a diatomic gas, the model is a little bit more complicated for a molecule because we have A and B forming a molecule, and we can think of this system very naively and classically, of course. I mean, this is not the truth at all, but let's just suppose that it's like a rigid rod, and at the two ends of the rod there are these particles, A and B, and they are just fixed at that distance and they just move around, okay? So here we don't have the problem of a particle moving, we have the problem of a solid moving. And you know from mechanics that you can write the Hamiltonian of every single one of these diatomic molecules as the sum of two contributions. So there would be the energy, kinetic energy associated with the center of mass of the system, and there would be some rotation energy, you know, associated with just the rotation of this thing around, which is a rigid body, but it rotates. So the center of mass part, you know, it's going to be the kinetic energy of the center of mass. Is going to be the kinetic energy of a fictitious particle that carries all the mass of the system. That's the total mass m here, and this has well, yes, it's in 3 dimensions. So this would be p1 squared plus p2 squared plus p3 squared. And the rotational part of the energy, well, this is generally going to include 3 more degrees of freedom because, you know, a solid can rotate along 3 different axes in principle. Thing is, this is not really a 3-dimensional object, it's a 2-dimensional object because this line here that connects the 2 molecules is really literally mathematically aligned, so it has no width, so it doesn't make sense to think about the rotation about this axis because there's no mass around it, okay? So we only have 2 rotational degrees of freedom, and remember the rotational contribution to a rigid solid in the simplest form is 1/2 some moment of inertia, again some constant multiplying things that are of the same form. So it's generalized coordinate squared, okay? So here will be some angular frequency around some axis theta and another angular frequency around some other axis phi, okay? So the sum of these 2 guys gives me the Hamiltonian of the system. And once again, if I ask what's the average energy per molecule, what I have to do is to do the same trick I did before, but I know what I'm going to get because the average of the kinetic energy of the center of mass is going to give me the same contribution. Let me just write it first, and there we go. So the first term is going to give me the exact same thing we had before, okay? So that's going to be 3/2 of kT, okay? Because we have 3 degrees of freedom here. We don't care about whichever constant that appears here. There is a 1/2 before, so we have 1/2 per each of these square terms. And the same thing happens with the rotational energy. We have a 1/2, we have the coordinate squared, and we have some arbitrary constant here multiplying, which will not affect the result. What we have here is 2 times 1/2 of kT. Each of these terms contributes with 1/2 of kT, just exactly in the same way that we learned was happening here in this example where you have the free particle, okay? Just because of the structure of the Hamiltonian and because we know the abstract result of the equipartition theorem. So what you have here in the end is 5/2 of kT, okay? So the internal energy of 1 mole of gas, of ideal gas, which is made of diatomic molecules in this case, is going to be the Avogadro number. Well, the Avogadro number again times 5/2 of kT, which is 5/2 of RT, which means that the heat capacity at constant volume, which is the partial derivative of U with respect to temperature at constant volume, equals 5/2 of R. Okay, and using again the generalized Major relation, well, not generalized, the basic Major relation, because we are in an ideal gas. This is Cv plus R, which means that Cp is 7/2 of R. Okay, which, if you remember, once again, was one of the results that we first introduced in the module. Now we are proving it as well. Okay, but however, this model of diatomic molecule, first of all, it's a classical model, so whichever way you put it, it's missing something quite important, which is quantum. But even if you go for a classical modeling, there's something very important that we're missing out here. The molecule is not just going to rotate as a rigid body, but actually the atoms can do small vibrations around their equilibrium positions as well. Okay, and this will complicate the Hamiltonian and will actually change the value of the heat capacities. And this is something we're going to discuss in the next